Welcome to remembrance-kjv.com. This is video number 8. In this video, we take a look at subtractive notation. Subtractive notation is the kind of number notation in which digits are represented as negative deviations from a base and its multiples. Let us try and elaborate what we mean by this. 11 is equivalent to 10 plus 1. 12 is equivalent to 10 plus 2. And 13 is equivalent to 10 plus 3. This is quite clear. What about 9? It is equivalent to 10 minus 1. In positional notation, mental arithmetics directs that it should be written like this. It is 1 bar 1, alternatively interpreted as 1 Vinculum 1. It is an equivalent of 10 less 1. This bar on top of 1 is the one that is referred to as the Vinculum, which simply means the bar. It denotes that the digit under it is negative. Note that it is not used in the same way as we use it in modern day schools and colleges. As for 8, it is 10 less 2, an equivalent of 1 bar 2. With regards to 17, it is equal to 20 less 3, which is 2 Vinculum 3. The same goes for 56. It is an equivalent of 60 less 4, a value expressed as 6 bar 4. It is possible for every digit of any number system to be represented in Vinculum notation. The numbers 1 through 9 can be represented in Vinculum format like this. History indicates that subtractive notation is mainly used in association with digits that form the upper half of a base. In base 10, we will be taking a look at numbers 6, 7, 8, and 9. If these that are in blue shade are removed, we are left with this setup. The upper half digits of a base form a group of numbers that are referred to as high complex numbers. The main reason why they are referred to as high complex numbers should be that the numbers are represented in a variety of formats so as to favor a desired number operation. In this video, we take a look at how they are represented using subtractive notation. In video number 10, we shall take a look at how they are represented using additive notation. And in other videos, we shall take a look at how they are represented using both subtractive notation and additive notation. Notice that the word complex is not used in a similar way we use it in modern day schools and colleges. Records of the use of subtractive notation in both history and prehistory are in abundance throughout the whole world. Let us take a look at Roman numerals. 4 is represented as IV. When a numeral representing a small digit is written prior to that of a bigger digit, it indicates that it should be subtracted. This is therefore interpreted as 5 less 1. However, the Roman numeral system does not respect positional notation. Representing 4 of the Roman numerals using mental arithmetic's Vinculum notation it is V bar 1. 9 is represented in Roman numerals as IX. This is interpreted as 10 less 1. In Vinculum notation, it is represented as X bar 1. From this, we can see that the knowledge of subtractive notation is recorded on Roman numerals. Let us turn towards South Africa and consider the number words of the Nguni languages. It's kunye, kubili, kutatu, kune, kuhlanu, isithupha, isikhombisa, isitshiyagalombili, isitshiyagalolunye, and finally, ichumi. Our concern is with digits 8 and 9. 8 is isitshiyagalombili. The last part of the word construct is mbili and is derived from kubili. 9 is isitshiyagalombili. Also, the last part of its word construct is lunye and is derived from kunye. Let us take a look at the meanings of these words. The number word for 8 is built from 3 words: isitshiya, galu, and mbili. Isitshiya can be translated to the phrase that which leaves out. Galu in Zulu means hip, and mbili is 2. The whole word can be translated to the phrase that which leaves out the hip by 2. The Zulu galu should be a borrowed word from the Shona garo. The Shona garo has 2 meanings. It means hip and also base. Isitshiyagalombili should therefore be translated to the phrase that which leaves out the base by 2. Translating into Vinculum notation, it's base less 2, which numerically is 1 bar 2. Also, the number word for 9 is isitshiyagalombili, and it can be translated to that which leaves out the base by 1. Translating into Vinculum notation, that is base less 1, which numerically is 1 Vinculum 1. Let us try and consider the addition of 7 and 8 using Nguni number words. Mind that I used Google Translator to come up with some Nguni statements that I'm going to use in this explanation. As a result, I might not sound as exact as the real Nguni language speakers may appreciate. So, 7 plus 8 goes this way. Isikhombisa kanye nesitshiyagalombili utolwane. The result is a matter of having an understanding of the meaning of the number words involved in the calculations. From the word galo, the base we get the word ichumi since the calculations are in base 10. The remaining words give the resultant phrase isikhombisa uchiye okubili. This is interpreted as 7 less 2. Isikhombisa uchiye okubili utolwane. That is kuhlanu or 5. So the result is ichumi nahlanu, which is 15. Let us translate the verbal calculation to its numerical equivalent. It's 8 plus 7. 8 is 10 less 2. That is 1 bar 2 plus 7. The solution is 7 less 2. 7 less 2 is 5. The result, therefore, is 15. Let us go ahead and add 69 and 8. 69 is 70 less 1, or 7 bar 1. So, it's 7 bar 1 plus 8. 8 less 1 is 7. The result is therefore 77. The multiplication of 9 and 8 using Nguni number words goes on as follows. Utolwane uma upinda-pinda isitshiyagalolunye nasisitshiyagalomibili. From the number words for 8 and 9, all word elements needed for calculations are available. The elements galu for the base, lunye for 1, mbili for 2, and chia for the subtractive notation. The base value amachumi is equivalent to the base ichumi less 1 chia kunye, or chia eyodwa less 2 chia okubili. As for the number of units, it's 1 kunye multiplied by 2 okubili. The result is 72. Amachumi ayisikhombisa nambili. Representing this calculation numerically, we have 9 multiplied by 8. This is 1 bar 1 multiplied by 1 bar 2. The number of tens amount to 10 less 1 less 2. As for the number of units, it's 1 times 2. This same calculation can be represented in this format. In ancient mathematics, the comma is not used to separate whole numbers from fractional numbers. It is used as a positional separator. It separates one positional quantity from the other. The symbol that was used in the same way as the modern day use of the comma is the semicolon. We are going to continue with ancient representation because mental arithmetics involves the use of partial values which ought to be separated by a positional separator. The tens value is 1 bar 1 plus bar 2. Separate by the comma, and the unit value is 1 times 2. 1 bar 1 plus bar 2 is 1 bar 3, and 1 times 2 is 2. 1 bar 3 is 7. Therefore, the solution of the multiplication of 9 and 8 is 72. This is the kind of arithmetic contributions we get from Nguni languages. Another yet to be questioned truth about subtractive notation is in time telling. Let us take a look at this diagram showing a clock. Let the red arm represent the minute hand and the blue arm represent the hour hand. When the minute hand is on the yellow side, the word past is ahead in time telling. When it is on the gray side, the word to is ahead in time telling. Counting of both minutes and hours starts from the 12-hour mark. On this diagram, it shows that the minute hand has moved 18 divisions from the 12-hour mark, and that the hour hand has just moved past the hour of 10. The time is therefore 18 minutes past 10. On the other diagram, the hour hand has passed the hour of 4, while the minute hand has moved 48 divisions from the hour of 12. Time, in this case, is not told as 48 minutes past 4, despite being correct to say so. We counted the remaining number of minute divisions left to arrive at the 12-hour mark. There are 12 divisions. The time is therefore 12 minutes to 5. Why say to 5? Because the hour hand is approaching towards the 5th hour. The minutes increase from 0 to 30, then begin to decrease back to 0. This clock was designed in a sexagesimal numbering system. However, it uses base 10 as its primary base. The first half increases normally up to 30, and the last half uses the idea of subtractive notation. The second part forms the high complex part of the sexagesimal base. If the sexagesimal system is to be represented according to how we call time, we have numbers 1 to 10, 11 to 20, 21 to 30. 31 to 40 is heard as a decrement from 29 to 20. A two-digit order of accuracy is enough to represent numbers of a sexagesimal numbering system, using the decimal system as a primary base. Then use a comma as a positional separator. 60 is represented as 01, 00. 31, which is 60 less 29, is written as 01, bar 29. And 40 is 01, bar 20. Next, we have 41 to 50 written as 01, bar 19 to 01, bar 10. Lastly, we have 51 to 60 written as 01, bar 9 to 01, 00. Let us state some of the observations we have made here. Clocks were designed in a community in which subtractive notation was in use. Subtractive notation is meant to favor mental arithmetic calculations. Mental arithmetic calculations have their basis in Africa, or Egypt. It can be inferred from these observations that clocks were originally designed in Africa. It is on the Egyptian or Ethiopian continent that the basic unit of time was first discovered. A proof of this argument is to be presented in later videos. It should therefore not be surprising that Thomas Fuller was quite abreast of all time calculations. Let us take a look at simple calculations in sexagesimal notation. Let's start with addition. It's 48 plus 37. 48 is base 60 less 12, and 37 less 12 is 25. So the solution is 01, 25. The order in which the brain will process the calculation is this. It's how much is required to add to 48 in order to make 60 the base. That's 12. Where do we get that 12? From 37. So 37 is reduced by 12 to arrive at 25. And the solution of the calculation is 01, 25. Let us take a look at the multiplication of 56 and 47. 56 is 01, Vinculum 4, and 47 is 01, Vinculum 13. The calculation is base 60 multiplied by the bracket of base 60 less 4 less 13, plus the product of 4 and 13. Using positional separator, this is the same as the bracket of the base less 4 less 13. Positional separator, 4 times 13. This gives the bracket of the base less 17. Positional separator, 52. Base less 17 is 43. The result is therefore 43, positional separator, 52. See how this last calculation has integrated mental arithmetics, subtractive notation, and algebra. It's quite compact. For your own information, algebra is supposed to be taught before a learner can master the multiplication table. It is taught as an aid to the learner to help him or her master the multiplication table. But in our modern day schools and colleges, a learner is first taught the multiplication table and then later algebra. If the case should be that algebra is supposed to be taught before a child can master the multiplication table, then you put it to mind, how long will it take the mathematics teachers to cover the mathematics content required for a general certificate in mathematics? Quite short. I promise you, very short. More details in videos to come. Do not forget to subscribe to this channel. Thank you, and meet you in video number 9.